Okay, a couple of announcements. So there was some confusion regarding the chapter numbers, and so I reverted back. When my materials were created with the older edition of the book, where the chapter numbers for 4 and 5 were flipped. Okay, the current edition of the book has chapter 4 as BJTs and chapter 5 as FETs, but I was still following the old pattern. And so students were getting confused, and so I flipped it back. So FETs, which we covered earlier due to the lab sync, is now renamed as chapter 5. There is no other difference at the student end, except in the class notebook early on. The first slide says it's chapter 5. That's all. Let's see. And then BJTs are chapter 4. So all right, so we stopped here, region of operation of the MOSFET, and then triode region, device operation, right there. Okay, so we saw in this N-channel enhancement MOSFET, we have to apply a voltage at the gate to create a channel. So unlike the JFET and unlike the depletion MOSFET, a channel does not exist. We apply a voltage at the gate to create a channel between the drain and the source. And once a channel exists, there is a pathway for the electrons to move between the drain and the source. Okay. So channel is a bridge that connects the two N plus regions. And now at this point, if you apply an external voltage between the drain and the source, shown right here, VDS, electrons will drift in response to that external applied voltage. Okay, hence the field effect. Make sense? So N channel permits electrons to flow between the drain and the source. In a depletion MOSFET, a channel is already existing. Channel already exists. It is created at the manufacturing process or during the manufacturing process. Okay. So enhancement mode MOSFET versus depletion. So depletion mode MOSFETs, similar to the depletion mode JFETs, a channel already exists. So depletion MOSFETs. And it's created during the manufacturing process. Okay, created during the manufacturing process. And so in an enhancement MOSFET, we apply a gate voltage to create a channel. In a depletion MOSFET, as with the JFET, the device is already set to be on because the channel exists. So we must apply a gate voltage to actually pinch off that channel to control that channel. Okay. Even though both devices are similar in many ways, the operation is not. The operation is very different. Okay. In a JFET, we do not have a gate oxide. There's no isolation. Okay. In a MOSFET, there is gate oxide, which isolates the gate from the rest of the substrate. Hence, the input impedance or the input resistance for a MOSFET is even higher than for a JFET. Gate current is DC gate current is technically just 0, right? There's an oxide that prevents any charge carriers from moving from the gate to the actual substrate. Okay, so for DC biasing, IG gate is always 0. Okay, let's see. So in the triode region, there are a couple of parameters. Let's see. And there should be, yes, it's not. Technical issues with sync. So in the triode region, let me just draw it out here. And this is similar to the JFET characteristics that we created, that we saw in the lecture and you created in the lab. It has a linear relationship, VDS and ID, the drain current and the drain to source voltage. Basically, the output side of the transistor has a linear relationship. So for varying levels of VGS, the controlling gate voltage so all VDS versus ID curves are linear. Okay. In other words, the MOSFET behaves like a resistor. When a voltage and current have a linear relationship, the device is behaving like a resistor. And so in this linear region, the MOSFET behaves like a voltage controlled resistor. Okay, voltage controlled resistor. This region is also known as the triode region. The name comes from the vacuum tube triode. Think back to week 1 where I spoke about vacuum tubes. We have 2 electrodes, an anode and a cathode. And then you inserted a third electrode in there to control the flow between the anode and cathode. That came to be known as the triode. So triode behaves. So this region behaves exactly the way a triode would work. Hence, triode region. Okay, let's take a pause. There's quite a few things to think about. Any questions? One remarkable thing is that the MOSFET and JFETs are completely different devices, different manufacturing processes. Operation is very different, yet the output characteristic curves are very similar. Okay, so again, so far so good. Okay, all right, so we have the linear region. In the JFET, we saw that the linear region, when you apply the drain to source voltage, current ID increases. It has a linear relationship, meaning it also behaves like a voltage control resistor. But at some point, the channel begins to pinch off, right? And the current saturates. And a similar thing occurs for the MOSFET. Okay, similar thing occurs for the MOSFET. In the saturation region, what happens is we have, of course, for all conditions for VDS, VGS is greater than the threshold voltage, meaning a channel has been established. Now, channel is established here with electrons. you apply a small increasing voltage between the drain and the source. So VDS has a slightly positive value. That would attract the electrons, current would flow between the drain and the source. Okay. At some point, actually, before we get to that point, let me recreate it in a slightly different version. Okay. We have a voltage between the drain and the source. We also have a voltage between the gate and the source. Okay. Before we begin the operation, before the channel is set up, the drain to source voltage is 0. So VDG is simply VDS minus VGS. If VDS is 0, the relationship between the drain and the gate voltage is negative, right? You have two different voltages, VDS and VGS. And so we can write an expression for VDG, the voltage between the drain and the gate. Now VGS crosses the threshold voltage, channel is established, and you apply a positive value of VDS. So VDS starts to increase. Okay. At some point, the difference between right here, the drain and the gate is going to keep increasing. And because of that applied voltage between the region right here, the channel starts to shrink. Okay, the channel starts to shrink. So slightly different causes, slightly different cause than the JFET, but the resulting effect is the same. When VDS equals VGS minus VTN, the threshold voltage, the channel is almost about to pinch off. When VDS increases to a level that is greater than the difference between VGS and VTN, pinch off occurs right there. Okay. The pinch off point depends on the fabrication process and the applied gate voltage and the threshold voltage. Okay. The threshold voltage itself, of course, depends on the fabrication process. And so the IV curves we had for ID versus VDS, they become saturated, or they reach a level of saturation. So if we had a linear curve for, let's say, some applied value of VGS, it saturates at a level. And unlike the depletion MOSFETs, the depletion devices, here, the VGS is a much higher value. I would say much greater than 0. Again, this is an enhancement type device or enhancement mode device. So if no voltage is applied, I'm just drawing a line right here. Yeah, this is fine. So this would be VGS equal to 0 volts. There's no voltage applied, then there is no channel. Okay, so it saturates at a level. And of course, there is a limit. We cannot just keep increasing VGS infinitely, right? So there is a limit depending on the fabrication process. And so the output curves are exactly, or at least I would say, very, very similar to the JFET. Okay, very, very similar to the JFET. Question? Yeah.
Why did you have two wells, right? And then do you have just one side that has too many volts, or is that
No, so it's the voltage differential between the drain and the gate. Between the drain and the gate. So VDG. And VDG depends on the applied VGS and the applied VDS. So as VDS increases, the voltage between the drain and the gate is changed. And that depletes the carriers from the channel. And because that depletes the carriers from the channel pinches off. So VGS, so to answer the question, VGS creates the channel. VGS creates the channel, right? When VDS is 0. But then VDS increases, let's say a random value, VDS is like 6, 7 volts, let's say, VGS. Creates a nice thin shallow channel below the oxide layer. Now VDS increases 0, 1, 2, 3, 4, 5. The value of VDS is still lower than VGS. At some point, it's going to increase where the difference between the drain and the gate, which is this one, that pinches off the channel. So on one hand, VGS creates the channel, but on the other hand, VDS pinches it off. So there's an upper limit on the voltages we can apply to every device. Okay. And when it pinches off, similar to the JFET, we would expect that the current would drop to 0 because the pinched off channel would be 0, but that's not what happens. The electrons are actually flowing through in response to the applied electric field due to the VDS, and then they get injected or pulled into, so from here, they get pulled into the depletion region. The depletion region is free of, it's not free of, sorry, it's depleted of free charge carriers. Free in the sense mobile charge carriers, right? The negative charge of the depletion region is from the immobile acceptor ions. But now you have free electrons pulled into the depletion region. So the current reaches, again, the constant level. And because of the positive voltage applied at the drain, the electrons are attracted to the drain and swept out. So current still keeps flowing. It does not go to 0. So at this point, electrons are pulled or injected into the depletion region. And once they are in the depletion region, the positive value at the positive charge or the positive voltage at the drain attracts the electrons, and they still keep flowing through. Yes.
So when VDS and VGS are the same, the potential across is 0.
Yes.
So there's no current. There's no free electrons to actually fill it.
No, the channel still exists. Yeah, at that point, it's not quite pinched off.
But any curving will be completely pinched off.
Yes. Yep. And that's what's shown like right here at this, in this one. So it just begins to pinch off, but there's still enough space for it to go through. So now current reaches a max level. It is no longer in the resistive portion of operation. It's in the saturation portion. Okay. Yes, Logan.
So VPN, is that just the difference between VBS and VPS?
No, VTN is the threshold voltage that is required to establish the channel. Yeah. And that depends on the manufacturing process. One key thing to keep in mind, nothing is to scale. Okay, we are talking about very small, tiny devices. With the current fabrication technology, we are approaching the quantum limit. We are approaching like basically transistors approaching the size of atoms. We're talking about like very few nanometers. Okay, few nanometers. Even though I've been working in this field for like a couple of decades now, it's still hard to get my brain wrapped around the idea that these transistors or these feature sizes are so small. I mean, I can throw out numbers and I can throw out prefixes like milli and micro and nano, but to even imagine that all of this is taking place at a level that we can't see is just, I don't know. It's hard. Sometimes it's hard for my brain to comprehend. Okay. So this is not to scale. This is very, very small and happens very quickly, a fraction of a second. Okay. All right. There are a couple of parameters that we need to talk about. So in the resistive portion, the triode portion, there are two equations we'd like to, let's see. Okay. All right. So when it is in the triode region, behaves like a voltage controlled resistor. Source current is equal to ID, and we can write an equation for ID in terms of the device parameters and the applied voltages. First is Kn prime, and then VGS minus VTN minus VDS over 2 times VDS, where we can simplify it further by writing and both of these, Kn and Kn prime, are known as transconductance parameters. And you can see why I keep repeating that it's a function of the manufacturing process or the way it is designed. Depends on the width and the length of the gate, right? Width and the length of the gate. And then of course, Kn prime can also be written as mu n, permittivity of the n-type material, and the capacitance of the oxide material, not oxide material, but capacitance of the gate oxide. Okay. So again, it depends on the manufacturing process. It depends on the design. Engineers and designers can choose, depending on their application, they can choose to design devices with different values of transconductance parameters. The units for these amps per volt square. Conductance itself is reciprocal of resistance. As amps over volts. Transconductance parameters Kn and Kn prime are amps per volt square. Okay. In the triode region, there's one more parameter, and that is on resistance. on resistance. Remember, it behaves like a resistor. And on resistance is given by actually VGS minus VTN. Graphically, of course, we determine this from VDS over ID. We don't have a MOSFET experiment in the lab for 346, but you'll be doing plenty of those in 347 next quarter. Okay. GM GM is given by the ratio, of course, is the reciprocal, so it's VDS. And to pick one point, you can, if it's a circuit, we can fix this at the Q point. Okay, at the Q point. Okay. Let's see. Saturation. Then let's talk about the different symbols that are used nowadays. Okay. So we looked at one MOSFET. What did we look at? We looked at a NMOS. It was an enhancement type or enhancement mode device. Okay. We looked at this one. But the operation of all is exactly the same, except the regions are changed. The NMOS, we created an N channel, right, between the two N plus regions. In a PMOS, you would have an N substrate with P type regions embedded in there, and you create a P channel underneath the gate. So PMOS. And then when you have PMOS and NMOS transistors in the same circuit, that's CMOS, complementary MOS. Okay, so from NMOS enhancement mode device, we also have PMOS enhancement mode. We also have N and PMOS depletion mode devices. Right, so those are the four primary kinds. Symbol for a NMOS enhancement mode device is shown right here. PMOS is right next to it. If the arrow is pointing inward into the device, then it's N type. When it's coming out, it's P. It's P type. Okay. And the depletion and the enhancement mode, you have 3 lines for enhancement mode, versus for depletion, it's a single line indicating the gate. Okay. So and you can see that, let's see, where is it? Oh, here. Depletion mode devices, NMOS and PMOS depletion mode devices. The gate is indicated by a straight single line, whereas for enhancement mode is 3 separate lines or 3 separate dots right there. Okay. These are pretty much standard. You will see a lot of these symbols used in many different circuits, different books, but these are pretty much standard. Okay, so the way I always like to teach is basically first you look at whether the arrow is pointing in or out. If the arrow is pointing in, it's NMOS. If it's pointing out, it's PMOS. If it's a straight flat line, one single line, then it's depletion. And if it's 3 separate dots or 3 separate short lines, then it's enhancement. Okay, those are the 4 main kinds of MOSFETs that you will encounter and use. Yes, you had a question. Which one?
Like A, B, C, D, rather 4 channels, OC.
Oh, this one, the terminal, the body, the bulk or the substrate. Yeah, so we had, right, remember in the basic construction here, body of the device. It's used to provide more control over the device. So it depends on, again, depends on the applications. So the bulk. Okay, three terminal notations are similar, except there is no body terminal in there. It's just a 3-terminal device, straightforward. On a little bit of a tangent, the JFETs that you used or will use in the lab this week is 3-terminal epoxy packaging. Before that, we used a different type of JFET that was no longer manufactured. It came in a metal can package, so round metal can. It had 4 terminals. The 4th terminal of the JFET would be connected to either the body and the metal can package. So in sensitive applications, you might want to shield everything and connect it to like ground separately. And so use that 4th terminal to do that. So that protects the JFET. Okay, I have about 10, 11 minutes left in regular time, and I'm hoping to go at least 5 minutes over time. So let's go into the main topic of 306, bipolar junction transistors. FET is a non-polar, unipolar, bipolar device. It's a unipolar device because you have N channel, you have one type of charge carrier. Diodes and transistors, or BJTs, charge carriers are both electrons as well as holes, hence bipolar. I know it has a negative notation, but the bipolar stands for there are 2 types of charge carriers. Current flows due to the movement of holes as well as electrons. Okay, hence the name. Bipolar junction transistors. Simply put, BJTs are 2 back-to-back diodes. Okay, you have 2 PN junctions connected back to back. If you have a PN and an NP junction connected, you have a PNP transistor. If you have a PN and NP junction, then it's a NPN transistor. Okay, so you have 2 kinds of BJTs, NPN as well as PNP. NPN transistors are the most common. For our explanation purposes, we will pretty much focus on NPN transistors. If the arrow is coming out, then it's an NPN transistor. If the arrow is going in, it's a PNP transistor. Okay. MOSFETs are with straight lines. BJTs, the lines are at an angle. Okay. And you'll be drawing these symbols over and over again for the rest of your academic career. So You'll have plenty of practice. Similar to the FETs, we have two terminals at the far end of the transistor, called the collector and the emitter, kind of synonyms of drain and the source, right? Source, emitter, drain, collector. So you have two terminals, you have current flow between the two terminals, and then you have a third terminal like the gate that is controlling the flow of that current. Okay. In this case, the gate is called the base. The operation is completely different. Okay. So for FETs and MOSFETs, we are relying on the effects of an electric field for the current to flow through. Here, it'll be more based on the PN junction current flow. This is an actual slice of a 3904 transistor. You can see this is the small device that you use, or it is there in the lab kit, right? So this is a cutaway portion. And this is the actual device right there. You see that? These are the thin leads. These are the connecting leads. I have to give Professor Chuck Bland credit for these images. So I borrowed it from him when he created from some of his classes. This is a close-up view of the actual transistor device. So this is the silicon die right here. And even in that silicon die, the actual transistor, the area is probably not even this much, probably smaller than that. This big pad, of course, is the metal contact that makes possible to access both sides of the device. Okay. From 30,000 feet, this is a very high level view or top view of an integrated circuit layout for a transistor, BJT transistor. Okay. Okay, so let's see the construction. So we said a BJT is two back-to-back PN junction diodes, but the physical construction is very different. Okay, the collector is the largest of the three terminals or the three regions. The collector region is the biggest. The emitter is by far the smallest. Okay, so this is the smallest. I particularly like this image because it very easily and very conveniently expresses what the difference in the size of the region is. So this is the biggest or the largest, and the other two are encapsulated within the collector region. This is very thin. And this is the most critical aspect of its functioning. Okay. It's the thinness of the base region that results in the unique operation of a BJT. Okay. So we have an emitter base junction right here. And then you have the collector base junction right here. The emitter base junction behaves like a true diode, like a true PN junction. So you forward bias it, and it behaves like a normal PN junction. Okay, base region is the thinnest and is the most critical aspect, and that allows the BJ to function differently than just two diodes. Okay. Also, the base is very lightly doped, very light doping. So there are not very many charge carriers. So physically, it's very small, and electrically speaking, it is very lightly doped. So not many charge carriers that are present. In contrast, the emitter is very heavily doped. Very heavily doped. Okay. A PNP construction would be exactly the opposite. We would just replace the N and the P type with the opposite materials. Here again is an image of a 3D illustration of the construction. The entire region that you see here is the collector. Epitaxy is a fabrication process. It's used to grow. It's called epitaxial growth of silicon. Okay, so don't worry about it now. Actually, don't worry about it unless you're going to take 434. Epitaxy is simply a process to grow silicon. Okay, N-type silicon. So this is a N-type silicon grown using epitaxial growth process. An entire region is the collector. You have an N plus region embedded here. That N plus region simply allowing it to make good contact with the N plus collector, with the N collector and the metal region above it. So it only serves as an interface. Okay. At its heart, it's still the same NPN device. Some authors like to use N plus to indicate emitter. Some authors like to use N plus plus. So it's N plus or N plus plus. Simply in the plus simply indicates the levels of doping. Okay. If you have an N-type collector and you N plus emitter, just means the emitter is highly doped in the collector. Sometimes some authors like to say collector is N plus compared to the base, meaning it's a higher level of doping, and the emitter is N plus plus to indicate an even higher level of doping. That's all it means. Okay. The three critical regions, again, collector is the biggest. It has average level of doping. Base is the thinnest with very little doping. And emitter is the smallest, but it has the highest level of doping. And because of which, the operation of a BJT is not as simple as just two diodes. Okay. You have the collector, base, and emitter. You have two back-to-back diodes. However, the operating modes depend on the external biasing, meaning the externally applied VCC, collector voltage, and VB, the base voltage, or VBB. Okay. This is connected between the collector and the emitter. And VBB is between the base and emitter. Okay. The respective currents and voltages are labeled as IC, IB, and IE, collector, base, and emitter current. And you can see here, like a FET and a MOSFET, the collector current and the emitter current are very close in value. It's 9 o'clock, so if you have to leave, you can feel free to leave. We'll continue until the next students and next people come in. Okay, so current flows between the two terminals, collector and the emitter, and then the base current IB controls the flow of current. Hence, IB controls IC. Okay, the relationship of IC and IB, the collector and the base current relationship, is the most important parameter for a BJT. And that is known as beta. Most important parameter for a BJT. Okay, and it's defined as the current gain. All right, so as I was saying, IB controls IC. The relationship of IC and IB is termed as beta and is the most important parameter for ABJT. It is a parameter that is specified on the spec sheet. Okay. Similar to the FET, again, the manufacturing process cannot control everything exactly the same. Even if you create the same exact transistor at the same time on the same wafer, right next to each other, like separated by like a few microns perhaps, the beta will be different. It is just not possible to control fabrication process at that level to be exactly the same. Because we are talking about doping with 10^17, 10^18 atoms. We cannot control it down to every single atom, right? And so beta is different for the exact same transistor. You could have two transistors in your lab kits, and the beta would vary wildly between the two. Okay, so it's always specified on the spec sheet, but it's also specified as a range on the spec sheet. The emitter current, of course, would be a sum of both the collector and the base currents. So IE is IC plus IB. And then the voltage between the collector and the emitter is VCE, and VCE is given by the collector base voltage and the base emitter voltage. For most operating modes, the emitter base junction is forward bias. VBE is forward bias. So if it's forward bias, what is the voltage for VBE? It's a forward bias PN junction. Should I go back and change your grades for the previous quizzes? It's 0.6 or 0.7 volts for a silicon diode. It's a forward bias PN junction. Okay. Basic operation is also illustrated here, where you have collector current coming from the top, base current coming from the left, coming together to form IE. Okay. Unlike an FET, there is no gate or there's no oxide separating the base terminal from the rest of the device, right? The base is part of the device. And that's one critical difference in the manufacturing of the two devices or the two transistors. In an FET, the gate is separate from the actual device or substrate. Here, the base region is part of the device. Okay. So in an FET, MOSFETs and JFETs, IG, the gate current is 0. Here it is not. IB actually has some value, but typically it would be in the microamp range. So IB would be in the microamp range. And quickly, I think I'm at 905. You know what? It's 905, so let's just stop here today. And I'll pick up here again on Friday. Monday is a holiday. And so no class on Monday, but I'm going to post Friday. There are some things going on. So I may or may not have class in person. I might either teach online live or I might post recorded videos. Quiz will be on Wednesday because Monday is a holiday. So it'll be on Wednesday. So long weekends, but you know, I'm gonna be working on the long weekend, so I'm gonna make you work on the long weekend too. But Tuesday, again, we have a lab for BJT, which is by far the longest lab. Okay, lab 7 is the longest lab of the entire quarter. Lab 8 is the shortest. And so actually, let me stop recording for now. So I want to give enough material so students are prepared before the lab.
Go back to the slide.
Sure, hold on.